Okay, enough of the people. Hi, my name is Danijela, and I'm coming from Rimac Technology. This is my first time I'm talking in front of this much people. I talk maybe in front of 10 people. So excuse me if I start jumping around. So today I'm gonna talk to you about how we developed software before on Nevera. And I'm gonna also tell you about Nevera and what are we doing now with the software and new components. Okay, is it going? No? Okay, it's going. So, as I said, I'm coming from Rimac Technology, and Rimac Technology is part of Rimac Group. Rimac actually started in 2009 from a garage, and with the BMW, where he made actually BMW electric vehicle. Then it started with a concept 1, continued with a concept 2 that is now familiar as Nevera, that started serious production 2 to 3 years ago. Today, we have more than 2,000 employees, and we are majority owner of Bugatti Rimac. So now, at Rimac Group, we have 2 complementary businesses. We have Bugatti Rimac that is developing and building hypercars, and we have Rimac Technology that is designing components for hypercars and for other OEMs, not just Bugatti. I'm coming from Rimac Technology, and I'm gonna talk to you a little bit what we do and how we do, and what we did. As I said, Rimac Technology is developing leading technologies. At the moment we are, so before, when we started with Nevera, we were developing 40 ECUs. ECUs is electronic control unit. So it's a unit, it's a microcontroller that is controlling one part of the car. So with Nevera, we had to start all from scratch. We didn't buy anything from anyone. We just started, we didn't know how to do it. And we had 40 ECUs, as I said, out of some 70. Now we are only focusing on 3 of them. But we are using our sister company, actually, Bugatti Rimac. We are using Bugatti Rimac to show what we can do. It was the same thing with Nevera. With Nevera, we were trying to sell ourselves and to show what we are capable to do. This attracts, of course, other automotive companies like BMW and Porsche, and we are doing components for them. Okay, so what we do, as I mentioned before, we do battery systems, high-performance batteries. We're improving them. We improve them from Nevera, what it was, and we have a lot of people who has a lot of knowledge that came from experience with Nevera. We are doing this from other OEMs, also for Bugatti. Vehicle controls, so we are developing software architecture that connects multiple ECUs into one for control of some other parts of the vehicle, like seats or windows, something like that. Then E-axle, this is where I'm coming from the project. It's a powertrain, and we are delivering high power and torque while maintaining a weight advantage. We are also the drive unit and the inverter. Everything is done in the house together with the software. And of course, some legacy businesses that are remains from Nevera that we need to maintain. So this was shortly about the company, what is company doing, because I figured out today when I was talking with some people, especially foreigners, they don't know who Rimac is, so I was a little bit surprised. So a little bit of company, and now actually what we did and how we're doing it. So Nevera, it was the concept, it started with the concept, it started with the idea of the 4 independent electric motors, and we had to do from start. We didn't know how to do it, where to start. I can tell you a small anecdote. When I joined the company, it was some 8 years ago, I joined as an embedded software engineer, and they just gave me a standard and said, implement this. There was like, okay, but how will this go into architecture? Which ECU will use this? How will be used? I didn't have answer to these questions. I had to come on my own to them and then align with other people's what do they think about. Now, it's going to be different. I'm going to explain to you later. What is also important for Nevera, there were actually, for the software development, we didn't follow much processes, but we did follow one, ISO 2626. It's a functional safety, and I'll later explain to you a little bit how this impacts software development. Okay, here's a small video to see what we did We were actually really proud of making this car. It was actually really fun making this car. It was fun when you develop something and it's working in the dyno, it's working on the board, it's working on the desk, and then you come to the car and it's not working, and then you need to debug it in the car. It was stressful, but it was really fun. So Nevera broke 23 world records in a single day. I crossed this number 23 with 20. I just crossed it because Nevera R improved in performance. Nevera improved in performance, called Nevera R, broke 24 world records in a single day 2 months ago. So where are we now after Nevera? So we figure out it was chaotic implementing all of this. We didn't have knowledge, we didn't have experience. A lot of people came to Croatia to work on Nevera. We learned a lot, and now we had to start with a new project. And how to start like this. So with the knowledge and experience, we figure out if we want to sell ourselves to other companies, we need to improve ourselves. We need to ensure high quality and reliability, and there we come to the processes. So I'm going to talk to you a little bit about the 3 main processes that we follow now in the software development for the vehicles and for the components for Bugatti and other OEMs that we follow and that we must follow. With this, we don't have much freedom with the software development. We must do what is needed and what is requested. A little bit about myself. I've been working as an embedded software developer, now working as a system engineer. And every time I'm talking with someone and they ask me, what do you do? I'm a system engineer, and everyone thinks I'm doing something with IT, I'm doing something with network, something, I don't know, with AVS. But it's the same name for, let's say, different, but the same kind of role. I do specify, I do maintain the system, but in this case, the system is powertrain of the car. So what I must do is I must specify the concept, I must specify the requirements, and see with the shareholders what needs to be implemented and what needs to be delivered. So regarding these 3 processes, we have, as I mentioned before, ISO 2626 standard. It's a functional safety standard that every component that's in every car needs to be, the software needs to be compliant with. We use this in Nevera, and I will tell you a little bit more about it. What are the issues with this standard? But it's the biggest nightmare for every automotive embedded software developer. Then we also introduced a new process, actually AUTOSAR platform. It's the standardized open software architecture. This came as a product from the 9 global global OEMs, most famous companies, Audi, BMW, Bosch, Continental. So they came with this platform for the open software architecture for the basic software. So for all the drivers, for the MCU, and some communication with the application. Here's one interesting quote for me. Why they did that. Because there's a lot of problem when you start a project, you have a microcontroller, and there's millions of issues, timing issue, performance issue, and you need to do everything, especially on some components, you need to do everything under tens of milliseconds, even less, nanoseconds. The third process that we introduced with our new project is ASPICE. It's actually process reference and assessment model that helps us to sell our product, because when the customer sees that we follow ASPICE, they know that every part of the every part of the software is there for a reason. I'll talk about that also. So first about AUTOSAR platform. It's to cooperate, the idea was to cooperate on standards and compete on implementation. And to be honest, this was awful. When we started introducing this, no one was satisfied because it's just a different mindset. So from the embedded software engineer who was writing a code in C, or some of them were doing some models in MATLAB, now they had to start learning new tools. So where you just like need to click, you click, but you can't find anything how to configure on Google. You can't ask someone. You can pay for some training, but they don't also answer to all of your questions because you need to work every day. It's actually, so people were really unsatisfied starting with this because they had to learn it. You got the document, and then you need to see, okay, this parameter means this, I need to set it on this value. So it took a lot of time, but now after 2 years of using this architecture, people become satisfied because it's solving some of the issues of the functional safety that we don't have to think about. So this layered architecture is showing is divided into application layer, where we are actually writing the application for our component. Then we have the runtime environment, that is interface between the application software and the basic software. And the basic software is the configuration of all the drivers that are used by the MCU. Next one is the, I forgot, functional safety. So functional safety is the international standard in the automotive industry. It has guidelines and requirements to develop safety-critical automotive system. I don't know if you ever wondered, like when you're driving the car and you know that the software is controlling some part of this car, like how safe is this? Will there be some bug? Will I crash because of the bug? That's where this functional safety comes into play. The thing with the functional safety is that you do the architecture, you develop the performance, you did everything, and the component is working how it's supposed to be. For example, I was working on the, as I said before, a powertrain, and we had a full performance, the car was driving, but then comes functional safety, where the functional engineers need to analyze every single signal, every input, every output, to see how it will influence in the end, the torque, how it will influence everything. So these are the deep analysis on already provided architecture and already system architecture and software architecture. So you can imagine you did something and now you need to do it from the scratch, because these analyses bring, okay, you need to do some monitoring around some signals, or you need to do some redundancy, like repeated measurement, or you need to put it in some kind of a protective memory. You need to use some part of calculations in the specific core of the MCU, not that one, this one, because on this one something else is there. You also have timing constraints that some faults needs to be detected in less than 1 millisecond, and this becomes a lot. The difference between before and now is before we were focusing on the performance. We wanted to have this performance, and now when we started the project, we start thinking about functional safety right away, so that we are not that stressed that much when it comes time to actually do this functional safety. So yeah, this functional safety, it follows V model. Also the following process that I'm going to show follows V model, where we actually have this parallelism between the left and right side, where a left side shows development and the right side shows testing. So every requirements are derived on the left side, where we have from the system requirements to the software requirements, to the software architecture requirements, and in the end to a software unit. Every this block must be tested before going on the upper part, before testing. So first we need to test software component to test software architecture and interfaces between the components, how they're working. After that, we can just test how actually this is integrated into the system. The worst thing here is that all of these things needs to be written down. Every decision, every concept. And we have, in the end, audit. Audit also checks the software. Where is software running some of the features, on which core, how much is rated, are there monitor, is the memory protected, which safety mechanisms are included, are we checking if we are having power. So there's a lot of things that needs to be developed. And it's even more work than the functionality that the component is supposed to have. Then we have ASPICE. It's a process improvement, and it also improves ISO 2626. Some of the customers, when they come, they say if our software development is following ASPICE, and if it's not following, they just like go away. But we start following this ASPICE, and it's also hard, because everything that is developed needs to have a reason why, needs to have requirement, needs to have rationale behind it. So you can't, there's not much freedom in how to implement something, or there is a little bit, but everything needs to be in the box. Everything needs to have a constraint. It needs to be strictly defined, the inputs, the outputs. So this also has an audit where external assessors comes and see what were the processes and how they were followed and what was the implemented, and in the end what was the tested, checking the test results against the test cases and requirements. So we start here with the stakeholder requirements, system requirements, and system architecture. So what is important here is traceability. This traceability shows that from the upper level, from the stakeholder requirements, system requirements to software requirements, we have a straight line, we have a trace, where did this came from, and why did this came from, and did it came from the customer, or did it came from some internal stakeholder requirements that we know from our knowledge, or that we know from some standards? And then we come in the end to the software requirement, and also, as I explained before, for ISO 2626 standard, how we do all of these testings. There are also here, it looks really easy on the paper, if you ask me, but when you start really doing this, where you first need to define, when you first get the stakeholder requirements, you also get your internal requirements, and then you start defining what software must do. It seems like, this is piece of cake, tester will take these requirements and they will test the software that is done based on these requirements, but then some change request happens, then some bug happens, and then we don't know which release is having what, and the time is really strict. So we are sometimes struggling, but we are managing. What this ASPICE process is showing to others is showing that we are able to meet certain standards for performance, that we are able to meet safety and quality. Okay, future. What actually future brings with the software development in the vehicles? So as you see, we had first 10 years ago when we first started, we just started how we know. It was like, however you know. Then we realized, okay, we need to standardize ourselves. We need to know what we are doing, what we are developing, because it will be easier for us later or harder for developers. It's a question. But I think it will remain like this. We need to have this structure to know how to implement what and when to implement, and it needs to be derived directly, and everything that is implemented must have its reason why it's implemented and where it's coming from. But the future brings more connected vehicles, it brings more vehicle autonomy, shared mobility solutions, vehicle talking to each other. I know that the main topic of this conference is AI, but I will not talk about autonomous driving. It's not my topic, but I know people are interested in that. But if you think about that, what can that bring? That could bring actually bigger concern for safety and security, all those topics that I was talking before, how this will influence. We're having a bigger hazard, more entry points for threats. So this is actually where we are starting to work to introduce artificial intelligence in our processes, to make sure that we specify everything how it's supposed to be, that software is doing what it's supposed to be, and that will make us more efficient or fast. With this help in the specification, with this help of understanding what we need to do, we can spend more time on the innovation and how actually develop things, the component that we are doing better. And that will be it. I was fast. When I was talking at home, this was 30 minutes, I was 20 minutes. Well, thank you. Is there any question? Feel free to ask.